Hello and welcome to the second video for Chapter 12, covering the topic of electrostatics. Here we're just going to cover a single section, section 12.3, which is the most computationally heavy section of this chapter, and it's all about Coulomb's law, which is a inverse square law, just like universal gravitation. Okay, so let's do a quick preview of the section here. You can see we are talking about the force between charges. If we're actually to measure that in a laboratory, we would probably use large charged plates, which are holding many trillions of individual charge carriers, those being electrons. But regardless, we'll often draw pictures of little balls that represent some small amount of charge. And historically, we'll talk about how Coulomb measured that force, which is right over here on the first relevant slide. Here's the force law itself. Okay. Of course, we'll talk more about that, about how to use it. Okay, I said it's like the universal law of gravitation. All right, what I meant by that is it really is. Now, if you don't remember the exact mathematical form of the universal law of gravitation, you should pause and go check it out, because it'd be rather easy to forget the first time you learn it, I'm sure. I'm sure it didn't stick in my head the first time, but I've seen it many times, and what I remember is that there's some constant in front, which is the gravitational constant, 6.67 times 10 to the negative 11. And then you have a product of masses in the case of the universal gravitation law. And then you have in the denominator the distance between those masses squared. Well, here you got some constant called the electrostatic constant. And here you have a product of charge. Yes, the letter Q represents charge, pretty standard letter for charge, okay? Lowercase q. Not to be confused with uppercase Q for heat flow. All right, this is charge. This is a new fundamental unit. This is really the newest fundamental unit to our very small elite group of fundamental units, which has included up to this point the meter, the kilogram, the second, most recently the Kelvin, and now number 5, really the last for us. There are a few others, but in an introductory physics class, we will stop at 5. And what do we have? Well, we've got the Coulomb, okay, the measure of charge. Technically, the actual fundamental unit is the ampere, which is the measurement of current, which is charge per second. So they're very closely related. One is a charge per time as a rate of charge movement, current of charge. We talked about current in a wire, right? But it could go either way in terms of actually learning the topic. Thinking about the building block, the Coulomb, it being analogous to the mass for gravity and inertia, right? The laws of motion. And so then we have the same relationship here. We have the quantity, the fundamental quantity that the particle can possess, the Coulomb of charge, the kilogram of mass. All right? But there it is, a brand new law, but man, it's got that same shape, that same mathematical form. Proportional to the distance between them squared, right? That'd be an example of a distance, by the way, right? R, like a radius, distance between, in this case, these two positive particles. So they're pushing each other apart. If they're further apart, they don't push each other as much. In fact, the distance matters a lot, because you double the distance, you cut the force down to 25% of what it was, because 2 squared is 4, 1 over 4 is your new force, okay? Proportional to the original. F naught divided by 4. We'll do some numerical examples with that. The book, just like me, and just about every physics person that's teaching this, every physics textbook, every web page, calls attention to this similarity. Calls attention to the fact that this is an inverse square law. It transcends just gravity and the Coulomb force, the gravitational force and the Coulomb force. It applies to things like sound intensity, light intensity, this idea of a spreading force, all right, or a spreading influence, a spreading energy, whatever it may be. Intensity, which is just wattage per square area, not square area, but per area. I'm getting off topic. Point is that the topic is that this inverse square relationship is a big physical relationship, and we have 2 important examples right here. Gravity, okay, electrostatic force, the Coulomb force. Notice it kind of goes by 2 names. We usually just always call this universal gravitation or law of gravity, but you'll hear me either call this the electrostatic equation or Coulomb's equation or Coulomb's law, all right, Coulomb's force. Sometimes it's the electric force, if I'm quickly describing it. All right, so that's the idea. All right, so let's get to it. Definitely check out some examples. So as I was saying, historically, this force between charged particles is not large for the amount of charge you can actually build up, which is kind of ironic because the actual strength of the force on a particle-particle basis is way more powerful than the gravitational force. About, I think, 1 trillion times or maybe 100 billion times more powerful. So like a 10 to the 10, difference. So I mean, just a huge difference in terms of the strength of the electrostatic force. So then why is it hard to measure? Like, why is it here that, so it says Coulomb measured how the electrostatic force varies with distance and the quantity of charge. Since the electrostatic force is so weak, wait, didn't I just say the opposite? He had to develop special techniques involving a torsion balance, okay? So what's the deal then? Well, it's so weak because it's hard to get a lot of charge to kind of work together, work in tandem, to actually get those effects of having like a reliable dipole, a charged up object that's reliably, repelling another one, especially because, what we're talking about is, experiments taking place over 200 years ago. And so, puts things into perspective in terms of, just like the amount of charge and the availability of the equipment and so on, okay? So, small force seemingly, right? Modern physics, as I said, at the submicroscopic particle, individual particle level, has revealed it's a much, much stronger force. So much so that when we look at the dynamics, the behavior of an atom, all the way up to the Bohr model of an atom at the turn of the 20th century, we can ignore the gravitational force completely because it is so weak, whether that's between protons in the nucleus or whether that's between the electron and the nucleus full of protons, whatever force combination you look at, gravity just doesn't make a difference, which is so remarkable because gravity is all that seems to matter when you get to the scale of planets, right? Or even us living on the surface of a planet, gravity is the dominant force by far, right? Besides, relevant non-conservative forces like drag forces and friction sometimes, being very important as well. So such an interesting thing, right? How the different perspectives, different scale can make such a huge change in the way we understand the physical world. Okay. Quick note about this idea of this torsion balance. It's neat to call attention to it. Similar experiments were conducted much more recently in the 20th century. The late 20th century, I think, where a very sensitive, basically column of quartz was placed with a similar situation where there was essentially a dumbbell, right, of two balls at the end. In this case, going back to the Coulomb force, these balls are going to carry charge. Okay, they're going to carry, most importantly, either a dipole in the sense of. Let's see if we can zoom in on this. I don't remember. No, but okay. If you look very, very carefully, but I'll just tell you that right here, this is a positive charge, and so is this. So they're repelling each other. So that's causing a twist. It would be a twist looking at the picture in the counterclockwise direction. So a twist kind of right if you're maybe looking down from this device up here, which is actually the readings, the scale with little notches that will actually read the amount of torsion that then can be converted to a force. All that said is that it is a repulsive force. There's a certain twist. Okay, the force is exactly the force we were talking about in the previous lecture video. It's a electrostatic repulsion force. Okay, they could be pith balls, for example. Again, referring to the previous lecture, which were the first two sections of this chapter. Okay, but I was saying that this same experiment was more recently done with gravity because all mass attracts other mass, and although we don't typically notice the attraction to any mass other than Earth, because Earth is so much more massive, we're attracted to the center of that spherical distribution of mass. Okay, so what I mean is that we don't notice a pull towards, say, people that we walk by on the street, right? Even though there is a tiny amount of gravitational force between any two bodies that have mass. So such bodies, just balls, were placed within the very similar apparatus, and there's a tiny amount of twist because of a tiny amount of horizontal force, okay, of attraction between the masses. So what does that mean? Well, that means that that tiny amount of twist was actually measured because the quartz, which was the replacement for the thin wire. In this case, think metal wire. But now think column of quartz, because quartz has this incredibly dependent structure and that will refract light differently, which just means bend light differently, depending on exactly how what forces it's experiencing. And so just a tiny bit of force will cause that structure to change in a reliable, measurable way. So a laser is being shown through that quartz, and as it experiences a tiny force, which creates a torque, which creates a torsion. Torsion is a displacement caused by torque. It's like a twisting, right? Like imagine like twisting in two opposite directions on a rope or someone's arm, right? That's a torsional type of distortion or displacement, right? Kind of like you have shear, which is like sliding off to the side, and of course you have extension and compression, other displacements. Okay, so all that said, that's the refined measurement. You could do that same much more accurate way of measuring down to very small degree changes with a quartz column as well. It's probably done before it was ever done for gravity. It was done as a refinement of this early experiment by Coulomb. But in this case, it's entirely mechanical. The wire, as it twists, will twist a very finely tuned and I would imagine well-oiled apparatus that will slide a tiny bit, which will show up as a little bit of twist. And with proper calibration, right? Then because you could then repeat this, right, with maybe gravity driving it or some other known force, maybe like a Hooke's law, sort of like a spring that is stretches a certain amount and supplies a certain amount of responding reaction spring force. You could calibrate the device and know exactly what a radial displacement corresponds to in terms of a force in newtons. There you go. You've got the Coulomb force. Okay, you've got a measurement. Okay, but that's one thing. It's great that this, scientist Coulomb was able to do that and say, hey, this is how much force there is between these two balls. But what does that mean, right? You got to know what's making the force, and he says it's charge, right? Because he knows that that was the idea. He built up static electricity somehow. But then, how much charge? What's the ratio? How do you actually get to that equation that I was showing you in the chapter, right? Because we haven't seen the slide that shows that equation yet. Okay, so that's what we're going to answer. So although he being Coulomb, could not measure absolute quantities of charge on the balls, okay? So he had no way of counting the number of electrons or even any inkling of the idea that charge was parceled out in individual chunks called electrons. That is a very modern idea that actually really kind of now is so common in our understanding of science because of the influences of quantum mechanics in the early the 1920s and 1910s. So it's a big deal, right? It's a pretty modern idea. Regardless, charge is a much older idea, okay? So Coulomb was able to measure the effects of this charge due to different relative amounts, okay? Because he's able to divide it and realize how much, right? So let's read these next few bullet points. By bringing two identical metal balls into contact, one charged and the other initially uncharged, right? So this is that neutral metal ball. This is conduction, right? So flowing. When they come into contact, they're going to equally spread the charge apart because all the electrons will reach a state where they're as spread apart as possible, which means if you leave them in contact for just a second or so, the electrons will be totally evenly distributed. It actually takes a fraction of a second. Okay, so Coulomb knew he had equal amounts of charge on both balls. He can now separate them and know. But he can then repeat the process. He could get a ball with exactly half that charge or 1/4 the original amount. Okay, he could then measure how the strength of the electrostatic force varied with those amounts, double, half, so on, right? So he can get down to whatever was his limit of having enough charge left, whether that's an 1/8 or a 1/16 or whatever. So you actually have a important then number of data points that you can look for the mathematical relationship between them, leading to an actual equation. All right. So it turns out the electrostatic force between two charged objects is proportional to the quantity of each of the charges. Okay. So it's the product of them, right? So when you say each, what we're meaning is it's the product, right? Because if you do one and then you do the other, you end up getting the product. Okay. It's directly proportional to both. Regardless, it is then inversely proportional to the square of each distance between the charges, okay? I shouldn't say each distance, it's just one distance, by the way. You can have multiple distances if you have multiple Coulomb forces. We'll see an example of that in just a minute, where we have 3 charges. We won't do more than 3. But then you imagine you have maybe a pole to the left and a pole to the right, or maybe both poles to the left or whatever, but the point is you just sum up the two, and the sum is the net force. That's the only force that matters, because that would be the force you would use for Newton's second law, because you can relate any force. Once you have it done, you can then say, I got force, F still equals ma, solve for acceleration, okay? if you're given mass. Now here's the value, right? Here's our new constant of the universe, right? These are just kind of coming out of thin air, I joke, right? The universal constant, as far as kind of modern physics knows, it is a fundamental constant, almost like a tuning number of the universe, tied in with its very origins in the Big Bang, I suppose. Now, the electrostatic constant is not precisely that. It's dependent on a couple other constants, and if you go 2 steps back, it's directly dependent on the speed of light, and the speed of light is a fundamental constant. So it's originally an empirical constant, which means one that was discovered through careful experimentation, repetition of those experiments, to find out exactly what was essentially the fitting constant on a function. In this case, this Q1 times Q2 over R squared function, right? Because it's essentially we're saying that this force, this Coulomb force, is either a product of Q1 or Q2 or R, right? And you either know 2 of the 3 every time, okay? And you always know K because K is a constant, right? And so that's what I meant. It's experimental or empirical, but more recently, because we're looking at this historical idea, this Coulomb law, right? But we're looking at it through a modern lens because we're including all these ideas of the exact units of the electrostatic constant, its relationship to other constants like the permittivity of free space, which we don't get into in this lecture, but is behind the scenes. This is all tied in with these ideas. Okay, so regardless of the number we will use, I said it was a big number. Indeed, it is. You can see it's on to the order of 1 billion. So it's just 9 billion, which is pretty easy to remember, I suppose. Because 9 zeros is a billion, just like 6 zeros is a million. So it's 9 billion, and then Newton force times square meters, so basically force times distance squared over Coulomb squared, right? So our brand new unit, the fifth joining the club, is the unit of the Coulomb represented by uppercase C, okay? And the variable is Q. All right. So let's do an example here on the slides, and then I'll do another example over on my tablet. So 2 positive charges, one with a value of 2 microcoulombs and another with a value of 7 microcoulombs, are separated by a distance of 20 centimeters. What is the magnitude of the electrostatic force that each charge exerts upon the other? All right. So by the way, if they're positive, would this be a force of attraction or repulsion? I bet you know. Okay. But you're going to plug the numbers in. All right. So heads up, there might be some things you're not familiar with. What the heck is a micro? Right? How did I even know to read the symbol as a micro? Well, the symbol is mu, which is a lowercase Greek letter. These are shown here, right? Mu could be either lowercase or uppercase. But here, looking at mu, what we read that as a scientific notation prefix for units for the metric system, is we read it as micro, and it represents 10 to the negative 6, which is a millionth. Okay, so it's 1 millionth. In other words, this is 2 millionths of a coulomb. Be 2 times 10 to the negative 6. Okay? So see if you can then plug these values in. You want to convert everything over to base units, because if we're going to be getting something with newtons out of Coulomb's law, we got to make sure that we're going to use, first of all, the electrostatic constant exactly as written, and we have to make sure that what we're plugging in for Q1, Q2, and R are going to be in units of coulombs and meters. See? Coulombs, meters. You don't see centimeters in here. You certainly don't see microcoulombs in here. Okay? All right. So hopefully you got your calculation done. Let's see what the answer is. 20 centimeter separation here. All right. This would be considered a fairly large charge. This would be like the type of charge you could achieve with a minimal amount of static electricity work, right? Rubbing things together. All right, plugging all the numbers in. Okay, this is just defining them, identifying them, and doing the aforementioned conversion. See, 2 microcoulombs, the 2 times 10 to the negative 6. All right. Now actually plug it into the equation. Okay, don't forget to square that denominator. And we get 3.15 newtons. Nice, excellent, right? That's a noticeable force, by the way. That's a force that you could absolutely perceive, right? So pretty significant, but again, it's a fair amount of charge, as I mentioned. Okay, so right here's the slide that talks about this idea that these forces, being gravity and the electrostatic force, have a lot in common. All right. There's this idea, and it really is fundamental. They're both fields. They both behave in this idea the same way. They just spread out in space. They create an influence at a distance. They don't need contact. They just continue to create influence, and as that influence spreads out, it's essentially spreading out on a imaginary sphere of influence. And you can then derive these equations precisely through the mathematics of calculus that Newton developed in order to publish and understand and make sense of his laws of motion, and then later used to apply to a publication on the universal law of gravitation that Newton also published, but was less entirely his. But all that aside, same sort of physics, right? So the physics, right? There's some universal idea here, which is pretty cool. Okay. And so, this is the type of stuff that physicists look for, and there's a lot of ideas that these forces actually were combined at some point at the very origins of the Big Bang, that under enough pressure and temperature, when conditions are so incredibly different from everyday physics, that these forces actually all are part of something, some universal property of space and time and matter. That we just don't quite understand yet. On that note, let's do another simple example with some calculations between charges. I mentioned we could put 3 charges, and when we do an example like this, we're going to do 3 charges in a row. We're not going to do anything with charges in a triangular configuration, or certainly 4 charges in a rectangle or square, because that requires a lot of trigonometry, which we don't do in this class. Okay? So in this case, with our one-dimensional 3 charges in a row, we're actually well set up to think about now not just calculating the magnitude of the forces with the Coulomb's law, right, equation as written, all right, relevant formula, plug it in there, relevant constant, plug it in there, all that, but actually really pay close attention to the direction of the force, because before it was always kind of an afterthought, like, oh, well, any other repulsives, are they both 1 point to the left, 1 point to the right? But now, if we're going to sum up the net forces from 2 charges on a single charge, we got to know if those 2 forces that we're summing up to get F net, if they're going to oppose each other, or if they're going to help each other out, right? If they will both add in the same direction. Okay, so 3 positive charges are located along a line as shown. What is the magnitude of the force exerted on the 0.02 Coulomb? Even more charge now. This would be read as 2 millicoulombs. No, 20. I don't know why I said 2 centicoulombs, but no one says centicoulombs. It's anything other than centimeter is kind of awkward. It just doesn't really flow off the tongue. But here it would be 2 or 20, right? 20 millicoulombs. Maybe just 0.02 coulombs is fine. Right? And then we got 0.1 Coulomb charge as well. So large charges, okay? All right, so is the magnitude of the forces exerted on? Okay, so at first it looks like we're ignoring the 0.04 completely, just kind of set the stage. So this one, despite all my talk about summing up forces, we're not doing that yet, but we will soon, right? We're going to find each one individually. Okay, so this should be the same as the previous example, right? Remember, same constants. Make sure you're putting everything in the base units. Graciously, this problem already has everything in coulombs and meters, so you don't have to do any of those powers of 10 scientific notation conversions. Just plug it in. Okay, so what'd you get? All right, well, you should get 4.5 million newtons, okay? And just to remind us, this is the force acting on the 0.02. So B is our kind of charge of interest, because think of it as it's the middle one, right? So we're focused on that one that's right in the middle, experiencing all the forces, okay? And we were asked only to figure out what the charge on the far left is doing to it. So in other words, we found the charge on B from A, okay? The force acting on B from A. By the way, Newton's third law absolutely applies here, and whatever force acts on B from A is exactly equal in magnitude to the force acting on A by B, and precisely 180 degrees pointing the other way. So in this case, the force on B would be pointing exactly to the right, okay? And then the force on A would be pointing exactly to the left. I know that because they're repulsive, okay? They're both positive charges. The forces are repulsive, okay? So there's our value. Of course, that corresponds to option B. All right. So now we're going to do it for, all right, let's see, 3 positive charges. So this looks like it's the same. Oh, there's a typo here. So what is the magnitude of the force exerted on the 0.02 charge by the 0.1 charge? But you can see what they're actually asking is they're asking for the charge exerted on the 0.02, but it should say by the 0.04. Okay, so there's a typo here in the question. All right, same sort of typo that I make, by the way, when I create instructional materials, because obviously there's a copy and paste and then change some values. So the natural question is to ask, what is the force on B by C? And that is what we're asking. Okay, and you can tell because if you look at the solution here, oh, sorry, I went the wrong way, gave too much away. But if you look at the solution for this one here, you can see that it is the other charge is the 0.04 charge. So the two charges being looked at are the 0.02, charge B, and the 0.04, Coulomb, charge C. So it's the force between them. Specifically, it's the force on B by C, which we know then is to the left, because it's a repulsive pair. It's a like pair of charges, right? Likewise, by Newton's third law, or you could just calculate it all over again, right, with the direction, you could find out that the charge on, we know that the charge on C is going to be this precise value, but to the right, okay? And by the way, if you think like, oh, shouldn't it be negative? That's because, well, we often call to the left negative, but here we're just identifying its direction rather than assigning it a sign, okay? All right, and that was option C, by the way. All right, so again, they had a little typo that just should have said 0.04. So now we've independently calculated both the charge on both the force on charge B from charge A and the force on charge B from charge C. Okay, so we've got two separate ones. They are pointing in opposite directions. One points to the right, the other points to the left. Okay, and they're not the same strength. We see that right now, right? Which should make sense because all the charges are different and the distances are all different. Okay, you could actually balance them out. You could like have it so you change the distance, but you change the sign accordingly, and the force ended up being the same. But that's not what happened here. Okay, so now finally, okay, we now want to know, okay, so what is the magnitude of the force exerted on, okay, so now another, wow, they really had a series of typos here. So what I can infer they're asking here from this first hint is that now they're asking for the net force. So now we want the magnitude of the net force exerted on the 0.02 Coulomb charge. So as I've said a couple times, we're just focusing on the middle charge, okay? And now that we've individually calculated the force from A and the force from C, we're gonna plug them in together, okay? So let's go over here. So that's the idea here, okay? So there's two forces acting on them, okay? They oppose each other, they act in opposite directions. So we have to take the difference. You could also assign a negative to one, right? By just defining the direction of your number line, which is to say the direction of your single axis. All right, so it's going to be F1 minus F2. All right, make sure you have this number for yourself, calculate it, got your answer locked in. All right, so it ends up being option E, because it's the 7.2 to the right, which we call the positive direction, minus the 4.5 to the left, which is the weaker one, but the negative one. And we have an overall net force that doesn't zero out, so that means that charge B would experience a non-zero net force, pulling it to the, rather, more like pushing it. Pushing it to the left. I say pushing because this one's trying to repel it, but it can't quite, right? Not initially at first. This one's strong enough to push it away. So B is effectively being pushed into a headwind, right, towards A. But it won't be pushed all the way towards A because these forces are absolutely distance dependent. And so although we could plug this into Newton's second law and solve for acceleration if we knew the mass of B, easy peasy, just plug it in. What we couldn't do is say find that acceleration, over a period of time or over even a certain distance because it changes, because as the distances change, the force changes, which means both these values, F1 and F2, would change, okay? But we can find it at any given instant, okay? And that will conclude the slides here, but let's head over to my tablet to wrap things up. By the way, we'll be talking about the electric field, that last slide that you just saw, in the third and final video for chapter 12, okay? So taking a look, you can see some notes, basically some kind of marked up annotated equations from a different physics class I taught using a different textbook and kind of a different approach. More math, all right, but here we're just touching on it. So we can see here is Coulomb's law. We can see the electrostatic constant. We can see some fundamental charges, which is often we care about just individual electrons and protons because we can make these great models of the atom, right, and solve neat problems about the atom, which helps us understand the atom. And so sometimes the charges that plug in for Q1 and Q2 are not going to be microcoulombs or a hundredth of a coulomb. or 2/100ths of a coulomb, like in the last example, which I was so hesitant to call centicoulombs. But instead, they're going to be these smallest possible units, which is 1.6 times 10 to the negative 19 coulombs. That's exactly how much charge every single electron holds. It doesn't vary, okay? It's quantized, it's how much charge they have, all right? And it's the fundamental charge, it's considered the fundamental charge. And it's negative because electrons are negative charge, okay? Protons, on the other hand, are positive charge, all right? But they carry the exact same magnitude of charge, 1.6 times 10 to the negative 19 coulombs, okay? Smallest piece you can have. That's interesting because you often see protons as they're shown as much bigger. That's true in terms of their mass. They're over 1,000 times more massive than the electron, but they are exactly identical in charge amount, which is interesting. Okay, so different masses, very different masses, but totally same charge. Okay, in magnitude, exactly opposite inside. Okay, tight. Okay, Benjamin Franklin called it sign, and we still do today. So let's just do one example to wrap up this video. Okay, so let's call this an example, which is not a very creative name, but what it's going to be is going to be a particle, a charged particle that's free to move. So we're just going to solve for that initial acceleration that I was mentioning before. So a charged particle that is free to move. Okay, so that's kind of our subtitle. Okay, so a particle with mass m equals 4.11 times 10 to the negative 12 kilograms. Okay, so base units there, right? Kilograms, no conversion necessary. Is placed as shown. Okay, so in the figure below, I'm going to show how much distances there are between everything and what all the values are, and I'll summarize them. Okay, so so far we just have its mass. All right, so let's draw that figure. Okay, so this will be our charged particle. Okay, so it will have our value of m. It's also going to have our value of uppercase Q. I know I said we typically use lowercase q, but sometimes we'll use uppercase Q for charge if it's a large amount of charge, such as on a conducting plate, like in a capacitor, or if you just want to call special attention to it. All right, and then it's going to be between two other particles on the number line. So here, let's get a faint number line, kind of running right through. All right, so this is going to be pointing in the positive x direction. Okay, and we'll have at this point, and we'll put this one right here, this will be at x equals 0, so our origin. And then over here, we'll put another value, another kind of point, which I'll just put down as 5, let's do millimeters, okay? And we'll put a charge located right there, all right, which we'll just have be Q, okay? Yeah, because I'll just have these two ones be the same, and it'll just vary the distance. Okay, which would be kind of a nice simple idea, because if you saw in the previous example, they had different distances and different charges on the charge that we're focusing on in the middle. We'll again focus on the charge in the middle. I'll have them have the same charge, different distances, but at a comparable complexity, I'm going to ask for a follow-up question, or the only question I ask for, which is the acceleration, which will require one more step. Okay, which is why I gave you the mass. So last thing though is we'll have our other particle. We're going to go ahead and put that one kind of to scale a little bit closer, and we'll label that as 2 millimeters. Okay, so x equals 2 millimeters. Very good. As I said before, same amount of charge. Okay, so I definitely have relevant values to list out. So I'll say values shown are Q, all right, which is going to be negative 9.11, all right, times 10 to the negative 3, okay, coulombs, all right, and then little q shared by both of the charges, which are fixed in place, which is why I'm not going to give you their masses. The only one that we want to consider moving is the middle one. And then q is then going to be, we'll have it be 2.00 times 10 to the negative 5 coulombs. Okay, so quite a bit weaker. Very good, okay? All right, and we got our millimeter distances, right? Distances is showing, we'll say with distances showing. All right, so as I said, I'm just gonna ask one question, but it will require you to find the F net force first. So my single question is, what is the initial acceleration of the central particle? Which in hindsight, I could have given a name like, particle 1 or something, but that's the question. That's all I'm asking for. To find it, you will need to find the net force, which means you'll need to find the Coulomb force twice, okay? Then you need to plug that into Newton's second law. Your force should be in values of newtons. And then from there, you can then just solve for acceleration in the typical units of meters per second squared. It's just a change in velocity. And it just will tell you how quick this thing will start moving to one side, okay? Again, just a snapshot in time. If we wanted to find it later, we'd have to recalculate all the forces, okay? And the rate of change is very difficult to pin down. But we can find it. We can find that initial acceleration, okay? All right, so go ahead and do it. And now I'm going to show you the values right now, okay? So let's bring up a calculator. Okay, so we want F net because F net equals MA. All right, and then we want A. There we go. Acceleration A. Should make that. Is that absolutely clear? Okay. So F net is going to be what we'll call F1 and F2. Okay. So I'm going to call them left and right. I'm adding them for now. You'll see that it'll just pick up a negative naturally. Okay. So let's see then. So the first one we have is going to be the one on the left. So we'll have our electrostatic constant in both cases, but I'll write it out in front. So I'm just going to write Coulomb's law as we know it. Okay, so it's going to be Q1, Q2. The order doesn't matter because, of course, it's multiplication. But for us, that's little q times big Q, right? But I want to plug I'll leave them actually as variables for now. So I'm going to say I want to plug in the numbers, but not yet because we can get the directions down. And then that's just going to be over 2 millimeters squared, which I will write like this. So actually plug the number in, but not convert it over to meters yet. Okay, that's the only one we need to convert. But would it be positive or negative if we're calling positive x to the right? Okay, well, these are opposite charges because you notice that our big Q is negative and the other two, the ones with a little value, little q, are positive. So it's all attractive forces. So it's going to be in the negative direction. All right. So this force would actually absolutely pick up a negative, which we would put in the front. Okay, and then the force from the right is a positive force. Okay, it is an attractive force pulling it in the positive x direction as defined. Let's put the k up here. It's the same little q and big Q. Okay, and then down below the distance is not the same. It's 5 millimeters squared. Okay, now we're in a good place to write out the numbers and of course plug them into the calculator. So our F net, which I want to solve first, and then I'll just solve A as a second step. I think it helps to do multiple steps here and see some values along the way. So if we look at F net, we can factor out a K. Okay, we can also factor out the product of little q and big Q. Okay, so all that's left, this is going to be over 1, because all that's left then is just going to be those two 1 over some distance squared values. So I'll put the positive 1 out in front. So I'm just pulling the 5 millimeters out in front, converting it over to meters, which is just 5 times 10 to the negative 3 meters, going to square it. then I'm going to subtract the other one. All right. Now this is going to be the bigger one because we're dividing by a smaller number. Dividing by a smaller number gives you a bigger number. So that means that F net is definitely going to turn out to be in the negative direction, which makes sense because it's closer to little q and it's attracted to it. Okay, so the attraction towards little q on the left, I should say, the attraction to little q on the right just isn't strong enough, right? So it's being overcome by the equal magnitude charge that's just simply closer, the one on the left. Okay. All right. So now, all right. So that's actually, that was more of a factoring step and conversion, but I need to plug in more numbers. All right. So we're going to use our 9 times 10 to the 9 Newton meter squared over Coulomb squared. We have the product of our two charges. All right. So we've got 2 times 10 to the negative 5 coulombs, and then 9.11 times 10 to the negative 3 coulombs. Okay. All right, and then just the business in the parentheses, the difference between the squares of the r values, which, because I'm coming out of space, always go ahead and calculate that first and plug it in, all right? So we're just going to give this a placeholder name. We'll just call it A, and it's going to be 1 divided by 5 times 10. Actually, open a pair of parentheses because I got to square it. So 5 times 10 to the negative 3, okay? And then square everything down there in the denominator. Move over to the next fraction, which is just going to be 1 over, again, open parentheses, 2 times 10 to the, again, negative 3, because we're still working in millimeters. Okay, and of course, square it again, because that inverse square law relationship. So A as expected is negative. The units here would just simply be 1 over square meters. So it's negative 2.1 times 10 to the negative 5, 1 over square meters. Okay, because we're certainly not in millimeters anymore. We converted over. So let's go ahead and move on over to the next page. I'm going to duplicate the whole thing, actually, just to buy us some more space. All right, let's copy it over. Okay, so now we can actually finish off our net force calculation over here in Desmos. So we'll put in our value for K, 9 times, oh, and I want to call this just uppercase F. So we can use it in our next and last calculation. So now, leading constant, 9 times 10 to the 9, positive 9, right? Right? It is, yes, that it is positive 9, right? And then the product of our two charges, so 2 times 10 to the negative 5, the smaller one, okay? All right? Always expect your charges to be, you know, small. This small or this or smaller, right? Like that fundamental one I showed you, 10 times 10 to the negative 16. Point is you're never going to see like 10,000 coulombs, just too much charge. Hard to get that much charge in one place because charge wants to cancel itself out to some degree. All right, there we have it. There's our product of charges, little q times big Q in that order, and then we'll just multiply by A, which again I just calculated independently for kind of ease of working with things here. All right, and like I said, because I temporarily had ran out of page space, although we ended up solving that problem. Regardless, our force is negative, because it points in the negative x direction, negative 3.4. We've kind of been working with a combination of 2/1 significant figures, so we'll round it to 2. I'm not picky about that. So 3.4, and then looking at the kind of subtle clustering of numbers, because Desmos, either I'm using it wrong or it's really hesitant to do scientific notation. Great for everything else, but you get used to reading it, and here we have, it's on the hundreds of millions, so it'd be 3.4 times 10 to the 8. Okay, and that is indeed in values of newtons. Okay, so finally, the last step, okay, because we found F net in the same way as the example back in the slides. Okay, so hopefully that repetition has helped a bit. But the last step here is something we haven't seen for a while, which is just using Newton's second law, although we absolutely did see that when we talked about the laws of motion. And so when you want to use Newton's second law to solve for acceleration, when you have done all this work to find F net and you already know m because you're just given it, well, of course you just divide both sides by m, okay? Because that isolates a. Okay, so our acceleration is just going to be the value we found, so the negative 3.4 times 10 to the 8 newtons divided by the given mass which I think was 4.11, times 10 to the, I just forgot, -3, -13, -12, okay? -12 kilograms. Excuse my messy writing there. All right. Regardless, let's carry on. So we're definitely going to get a negative acceleration. Acceleration is always parallel to F net, okay? So that's exactly where it should be pointing. And it just means that at the moment that the system is released or starts or something, that big charge in the middle is just going to start moving to the side. And everything being really tiny here and highly charged, the acceleration is going to be huge, okay? There are incredibly large accelerations like this, especially with, fundamental particles, these huge values. So what do we have here, right? We're going to get, just by looking at it, you can kind of do a little trick here. You can say, oh, you got a power of 8, so basically 8 zeros. You're going to be dividing by a power of -12. Well, dividing by a negative is the same as adding a positive in terms of powers of exponents. So this is just going to be 8 plus 12. So we're going to get a power of 10 to the 20. Okay, so that's a big acceleration. All right, so let's go ahead and actually plug that in. So if I want to solve for acceleration, I shouldn't have called that placeholder variable a. I'm so sorry about that. We should have called this like something that absolutely did not confuse it with acceleration. Let's just call it, because it just represents the distances squared, I'm just going to call it f, okay? Which means we have to fix this equation over here now, because it needs to have the same variable in it so that Desmos can actually do its calculation, right? Like a program. Okay, so now we will use the letter a, all right, which we need to reserve for acceleration in this example, all right, which I should have done, and divide by m. We haven't used m yet, so I'm just going to be plugging it in for the first time. 4.11 times 10 to the -12, all right, and there we go. All right, so we have our value. I guess I'll write it down here. So our final answer, acceleration, is -1.2 times 10, right? And we should have, as I said, something on the order of 20. Okay, did we work that out correctly? Okay, because I have, yeah, so 3.4 times 10 to the 8. Okay, and then because I'm not looking at, oh, I see what I did wrong. You all see it? All right, so that's not an exponent. That's just minusing 12. There we go, -12. Excellent. So, by the way, if the number is big enough, Desmos will finally resort to scientific notation, but you can see it seems hesitant to do so. Okay, so that answer was wrong, just kidding, because of a typo. But now we have the correct value, -8.3. Let's stick with 2. So the 7 would round the 3 up to 4. So -8.4 times 10 to the 19. Okay. Now, if you're wondering why I got 19 when I seem so confident we get 20, is because I was just looking at the powers of 10, and so that's true, right? You would get 10 to the 20, but you would get exactly 10 to the 20 if both of the coefficients in front were the number 1, but of course they're not. And 3 over 4 is less than 1, which brings us down to 10 to the 19. If we're kind of getting technical here about exponents, which it can be a real time saver and a really great way to like kind of think about this and have it sink in. Okay, so there you go, an example with the Coulomb force and Newton's second law. All right. So that definitely concludes this second video for Chapter 12. The third video will cover electric fields and electric potential, otherwise known as voltage. I hope this video on the Coulomb force has been interesting and informative. Thank you so much for watching.